In this video, I want to discuss this operation called convolution, and it's an operation that we can use to detect whether or not a feature is present in an image or not. And so what I mean by feature is we can apply a particular filter or a kernel, like for example this one. We can apply it to an image, and we can see the response, also called an activation map, of applying this filter to the image. And this kind of corresponds, and you can think of this intuitively as being a feature detector, and I look across my entire image, and the values that I get back represent how, if this where is this feature present, and how strongly is it present. And so we'll be discussing how we can do this, and I'll show some different examples, like there are different variations that you can do with this. It's actually an operation that is borrowed from signal processing and electronics, and so we're applying this in the sense of an image. And actually, in some ways, you can think of an image as being like a 2D signal, and there's like intuitive interpretations of how you can think of that. Sometimes it's useful to think of it like a signal. Anyway, so what happens is, and I'll have examples in the next few slides, but essentially we have the window is this filter or this kernel, and essentially we just kind of smack it on top of the image, and we compute an operation, and we just slide that window across the entire image, and we're computing a new value every time we slide it over. So this is called the sliding window approach, and the reason that we do this is because we want to compute these local features. So if we're detecting something like lines or edges, we don't really need to have the information on the entire image about this. We just have to look at a small local patch or a small local window to determine if there's an edge in this patch or not, and we just kind of keep sliding that over. And this is, quite clearly, the heart of convolutional neural networks is convolution, so that kind of makes sense. And when we get to those, you'll see that these features or these filters and kernels are actually learned during the training process. So we don't hard code these anymore. We let the network learn what these should be. And before we had convolutional networks, convolution was actually still quite used for things like edge detection, as we're going to use it for. You can use them for blurring, you can use it for sharpening, and there's tons and tons of other tasks. Just by changing the values of this kernel, you can make, when you apply convolution, you apply the same operation. Just by changing the values in this kernel, you can do different things to the image. Okay, so here's an example of what happens when you apply a convolution. So here's a particular filter that I'm applying to an image, and when I apply this, when I can involve it with this image, I get this thing back called an activation map, and it tells me how strongly I'm detecting something in this image. And so you can see that the darker something is, then that means that I'm not having a high activation. But the closer to white something is in the activation map that I visualized here, the stronger it's present. And so you can see, like over here, this horizontal line seems to be or this vertical line, I should say, seems to be very, very strong. And so that makes sense, because this filter, turns out, is actually meant to detect vertical lines. And so I can build one that can detect kind of horizontal lines as well. So you can see, like over here, this part is kind of horizontal, and so it's being detected quite well. So that's kind of what convolution is doing in the end. And so instead of doing something like detecting different kinds of the orientation of lines, we'll see that convolution will actually work to detect different, more higher level features. So like maybe we'll have later in the deeper networks, you'll see we'll have a feature detector for something like eyes or like noses or paws or something like that. So how do we actually compute convolution? So you can kind of think of it as a dot product in a sense. So what's going on is here's our feature or our filter or kernel that we're trying to detect in this image. And so what you do is you take this little 3x3 patch and you place it on top of your image. And so this dark gray is like the patch that I placed on top of my image. And what you do is you kind of like take a dot product, where you take the dot product of the values in the image with the values of the kernel or filter. So, for example, to compute this value, I take 1 times 99 plus 0 times 98 plus -1 times 99 plus 2 times 99, and so on. And I keep doing that, and I add them all up together, and I get the value of 12. And now that I have a value, where do I put that in the image? Well, usually you replace, or when you compute the new image, you replace all of these with a single value at the center of the kernel. So it's important that you use kernels that have an odd dimension, so like 3, 5, 7, 9, or and so on. And what happens is you can actually figure out you can do some math and figure out what my output image, the size of my output image is going to be given the dimensions of my input image and my kernel. And so this will end up being a 3x3 because there's only 3 different places for each row and column of the image where I can, or for the width and the height where I can place this in a valid position. So after I compute this operation, I put in a value of 12 here, and then I slide the filter or the window over by 1, and then I can do the same operation again. And so I slide it over by 1, and now you see that I have new image values I'm considering. Now I again take the dot product. 1 times 98 plus 0 times 99 plus -1 times 0, and so on. And that gives me this value, right? And then I slide over again, and then I get another value. And then, oh wait, I'm at the edge of this image. What do? Well, then I just go down a row. And so again, I do this and compute this like dot product like thing, and then I replace this block with just the center with the value to put this at the center. Okay, and then if I keep doing that, then I get this out. And here's what's called my activation map. Okay, so you saw that in the previous example, the activation map was actually smaller than the input image. But that's maybe not desirable in some cases, where so maybe you want to apply convolution so that the output activation map is the same as the input image. Did you want to keep that kind of spatial dimension? And so there is a way you can do this. And what you do is you pad the outside of the image with zeros. And so when you do this, you can figure out how many zeros you need to add to the border of the image so that you can pad it, and so that the output dimension is going to be the same as the input of the image. So in this case, you see that my image is a 5x5, and my activation map is also going to be a 5x5 if I add some padding. And so I just incorporate the padding when I'm doing the convolution. So my first patch I'll put over here is going to be, is going to include this kind of 0 padding. And so then that way the center pixel is going to be always at the top, and I can keep doing this, and I can fill in the rest of my activation map. And the nice thing about this is my activation map is the same size as my input image, and this you're going to see later on that this is actually quite desirable. And people still debate about whether or not should you use padding, should you not use padding, Anyway, so there's another kind of convolution that I want to discuss. These are called strided convolutions, and so you can see that I also have 0 padding here. But the difference between regular convolutions and strided convolutions is how many steps I move. So in the previous examples, when I'm done with for one patch of the image, I just move over to the right by 1. But with strided convolutions, I don't necessarily need to move over to the right by 1. I can move over like by 2, for example, and then compute a convolution. And so this kind of has two different features, or two different properties that is going on. So kind of the first thing that's going on is that I'm still computing convolution. I'm still detecting if a feature is present in an image or not. So that's desirable, obviously. And then the second thing that I'm doing is I'm also reducing the spatial size of my image. So there are also cases where I want to reduce the spatial size of my activation map, and we'll see this more later when we get more into convolution neural networks. There are times where this is also desirable, and so we'll be discussing what is appropriate for which is appropriate, whether I should keep the same dimensions or scale down. We'll be discussing that in the next few videos, but this is also something that I might want to do. So instead of moving over by 1 with strided convolutions, I move over by how many my stride is. So if my stride were 2, I'm going to jump over by 2 pixels. So initially I was here, I just jump over by 2, and I jump over by 2 again. This produces a strided, and I can kind of keep doing this, and that will produce a strided convolution. Okay, so I'm going to stop right here and just do a really quick recap. So convolutions are at the heart of convolutional neural networks, and kind of the whole point of convolutions that we'll be discussing for the purposes of convolutional nets is that we wanted to see whether or not a feature is present in an image and how strongly this feature is present, and also where it is in the image. And so we have some filter, some kernel that represents our feature, and then we convolve it with our image, and the result is what we call an activation map, and the activation map tells us, this exact information. Where is this feature present in the image, and how strongly is it present there? So that's kind of the heart of convolutional neural networks, and then now we're actually going to discuss convolutional nets actually in the next video.